So in our next video, we're going to be working on the integration formulas and practicing some integration problems. So please be sure to watch Antiderivatives Part 2. Hi, this is Mrs. Evans, and this is Part 1 of the lesson on antiderivatives and indefinite integration. Last semester in calculus, you learned a lot about the process of taking a derivative, or differentiation. Well, this semester we're going to be looking at working with the opposite of taking a derivative. So we're going to be looking at anti-differentiation. So to get us started, what I want you to think about is something that you learned about quite a while ago. I want you to think about what an inverse is. When you think about an inverse, you might think about it is the opposite. But what's important to know about an inverse, it is actually an opposite process. And it is a process of undoing. So when you talk about adding, subtracting is the opposite process, or it will undo adding. It also goes the other direction. Adding will undo subtracting. Multiplying will undo dividing, and dividing will undo multiplying. So they are inverse processes of each other. So last semester, when you did a lot of things with derivatives, you used the process of differentiation. The inverse of differentiation, or the process of undoing differentiation, is integration. And just like the other ones, it goes the other direction. Integration will undo differentiation. So basically, integration is the opposite of differentiation. And so to get us started with that part, I want to show you a few things. First of all, there's two different types of integrals. There is a definite integral and an indefinite integral. A definite integral is going to have a definite answer. It's going to give you something like 12 or -10. An indefinite integral usually gives you an expression as an answer. And so basically you don't know what the exact answer is, and there can be multiple answers. As a matter of fact, there can be an infinite amount of answers. So what it would look like in the beginning is this is what a problem might look like. And you'll notice there's a new symbol, and it's got that kind of squiggly S in the front. But both of these are integrals. The one on the left is a definite integral, and the one on the right is an indefinite integral. And what you'll notice about the difference between the two is that this one has numbers at the top and the bottom of that kind of fancy squiggly S. Well, when you find the answers to these, which we will be doing later, is this one is going to have a particular answer. If I can get that answer to come up. For example, in this one, the answer to it is 15. But over here, the answer to this one is actually an expression. It's the expression x cubed over 3 plus 2x plus c. Now it might look a little bit more difficult, but actually you have to find this answer, this expression answer, before you can actually get to this one. So we'll be doing a little bit with that. But this entire session, we're going to be mainly just working with the indefinite integrals. So we're going to be working with what is called anti-differentiation. So here's something I'd like for you to put in your notes. The indefinite integral is called the antiderivative. So we're going to be working with indefinite integrals or antiderivatives today. So also in your notes, I want you to write down this weird looking equation. And I'm going to tell you how you actually would read this equation. So after you get it in your notes, I want you to look at this part right here is read like these words down on the bottom. The antiderivative of f, the antiderivative of f with respect to x. So it's with respect to x. That's how it's read. So y equals the antiderivative of f with respect to x. Now each of these parts have different names, and you're not really going to be responsible so much for the names, but you kind of just need to know what they are. So the first thing is that squiggly s, and that squiggly s is called the integral symbol. If you see it, you're going to be taking an antiderivative. The f of x that's on the inside is called the integrand. It's basically the function that you're taking the antiderivative of. The dx, which you learned last semester, is actually called a differential. In this case, is also called the variable of integration. And what it mainly does is it tells us what letter these functions are going to be with respect to. So it's going to tell you if we're in terms of y's, in terms of t, in terms of x's. So a lot of times we're using t's and x's, but we need that to know which variable we'll be using in the problem. Now the answer comes out to be a capital F of x, and that capital F of x is actually an antiderivative of little f of x. Now what I want you to notice is something very important. I said it is an antiderivative. What that means is that there is not a single answer. So if you'll notice, I didn't say that it was the antiderivative. If I said it was the antiderivative, that would make you assume that there was one answer. An antiderivative actually gives you a family of answers. And where that family of answers actually comes from is this constant at the end. That c is a constant of integration. So it's going to be a number, but that number is going to change. So it's not going to be the same each time. So if you can get all of that down in your notes, a lot of this will make more sense as we get to the end of this lesson and into the next one. So before we get into antiderivatives, I want to do a quick review. Do you remember taking your derivatives? The main rule that you learned in the very beginning was the very popular power rule. And what the power rule did for us is it told us this. If we are taking the derivative with respect to x, notice how we say with respect to x in this case, and we said that when we were talking about the antiderivative. If we're doing the derivative with respect to x of a power, an x raised to a number, what we ended up doing is we ended up multiplying by the exponent. So we multiplied the whole thing by the exponent, and then we subtracted the exponent by 1. So we brought the exponent down by 1. So if I had f of x is equal to x cubed, when I took the derivative, I would get f prime of x equals 3x squared. So I brought down my 3, and my power on, or my exponent on the power went down by 1. Now I'm going to mention this quite a bit today, because remember when we were talking about inverses? When we do the inverse of taking a derivative, and in particular this power rule, we're going to be doing the opposite of multiplying, and we're going to be doing the opposite of subtracting. So we're going to come back to this in a little bit. When you're finding an antiderivative, it's a lot like playing Jeopardy. You have to think backward. So if you've ever watched the game Jeopardy, they actually give you an answer and you have to come up with the question. Well, we know our derivatives really well. So what we're really going to be doing is we're going to be looking at an answer and saying to ourselves, what function was the original function? So that way when I take the derivative, this is what I get for my answer. So let me show you what I mean by that. If I told you that f of x was equal to 4x cubed, and I wanted you to find capital F of x, which is the antiderivative of 4x cubed dx, you have to think this to yourself. You have to think, what function, when I take its derivative, will give me 4x cubed? So you notice how that's like Jeopardy? You're thinking the other direction. So, what function, when I take its derivative, will give me 4x cubed? Well, if you came up with capital F of x is equal to x to the 4th, you have one answer. Because if I took the derivative of x to the 4th, I would get 4x cubed. But the question is, could there be more than one answer? Well, I want you to think about this. What I want you to think about is, what about x to the 4th plus 5, or x to the 4th minus 3? So take the derivative of each of them. take the derivative of x to the fourth, take the derivative of x to the fourth plus 5, and take the derivative of x to the fourth minus 3. If you took the derivative of all three of the problems I gave you, which no matter what was the same answer, you still get 4x cubed. So the point is that it doesn't matter what constant is at the end, or if there actually is no constant, you are going to get the same antiderivative. So when you are taking an antiderivative, you must take care of the fact that there could be a constant at the end, this constant of integration. So anytime you take an antiderivative, you must add a plus c. Very important, so put that in your notes. As a matter of fact, on an AP exam, they'll take off a whole point if you don't do that. So we are going to practice some, but before we get to practicing, I want to have you just remember some of your differentiation formulas. Right, we're going to, on the left I have some of the generic stuff, and on the right I have some examples. But we're going to go through really quickly some of them, and what we're going to start with is the very bottom. We're going to look down here at the power rule. Here's what you need to remember about your power rule. We multiply by the exponent and we subtract the exponent by 1. So in our example over here, we got 13x to the 12th. And our generic is bring the n in front and subtract the power by, or the exponent by 1. Another part that was important, that's going to be really important for antiderivatives, is when we are doing the sum or the difference of two functions, what we can do is we can actually just take the derivative of each part. That's really important to know because we can do the same thing with antiderivatives. If we have to do the antiderivative of a sum or a difference, we can take the antiderivative of each part. Question is, can we do that with multiplying and dividing? Well, we couldn't in derivatives, so what you have to realize is you can't do it in antiderivatives either. So in our example over here, we just took the derivative of each part. What's important about this next one right here is called the constant multiple rule. And what it states is if you're multiplying a function by a constant and then you're trying to take the derivative, that really what it is it's the derivative of the function and the constant is just left in the front. So that's all it is. The constant's still left out there. And we kind of skipped through that a little bit when we did our derivatives. And let me show you our example over here. When we had a 3x squared, what we just got in the habit of doing is taking 2 times 3, which gave us 6, and then we subtracted 1. And that's okay. That's the easy way to do it. But what is really happening is that 3 is in the front, and you're doing the power rule. And so you take the power rule of x squared and you get 2x to the first. Then you're able to multiply the 3 times the 2. So although you don't have to do it that long way, that's really what's happening. Now this one, this derivative of kx, the answer in this case is just k. And some people don't know why. So I wanted to remind you real quick of why. So look at the example. On the example you have a 7x to the first. If I take 1 times 7, I get 7. And if I subtract 1 away, I get x to the 0 power. Well, what you have to remember back from a long time ago is anything to the 0 power is equal to 1. So this is really 7 times 1, and that's why you get 7. That's important to know for antiderivatives also. The last rule that we're looking at is this top one, and it's the derivative of a constant. Well, what we came up with was the derivative of a constant was 0. Do you remember why? Well, here's the example. If you look at the example of f of x is equal to 3, that really means it's 3x to the 0 power. X to the 0 power equals 1. So do your power rule. 0 times 3 is 0 times x to the negative first power. Well, 0 times anything gives you 0. So what your final answer is just 0. So the reason why all constants end up being 0 is because you're multiplying by x to the 0 power. And when you apply the power rule, that basically wipes everything out. So we're going to work on some integration formulas and some practice problems. So be sure to watch Antiderivatives Part 2.